Hello everyone, so welcome to the second part of chapter number 8. So guys, this is the second video that you should be watching for chapter 8. You must have watched the first video first. So here guys, we're going to talk about genetic disorders, and we're going to talk about their inheritance pattern. You're going to see 2-3 questions guys on your exam from this, and also of course on your study quiz this week. So to begin with guys, we'll talk about the basic pedigree. We're gonna learn on how to analyze these. We did talk about what we actually mean by each of these things in the first video, but this is just going to be another way to read them. So what we can say here is, if we want to form sentences and you want to say out the story behind pedigree A, what are you going to say? We will say that there are 4 kids who had parents and then they were grandparents. So this is on the top is your generation number 1, this is generation 2, and this is generation 3. Okay, what we can say here is that the grandparents had no disease, so because they're unshaded, and this is the the grandfather, this is the grandmother. And then they had 3 kids. Out of 3 kids, 1 was a normal male. Now by normal male, we just mean that did not have a disease, okay? Let's say, imagine this, we are talking about any particular disease. And then we can see here that this is the daughter who is also not affected. And then there's another daughter who actually got affected, and that's what is represented by this shaded red color. And then we can say that these 2 parents had 4 kids. Out of those 4 kids, 2 daughters were not affected, 1 daughter was affected, and son was not affected. So you should be able to break down this pedigree into what I just said. So you should be able to make up this story. So you could be asked a multiple choice type question on your quiz and exam, where you can ask you, okay, tell us that in the second generation, which individual is affected. So you will say in our second generation, Roman numerals for generation, second generation, kid number 3 or member number 3 is affected. So this is number 1, this is number 2, this is number 3, and this is number 4. So and also in this generation, this is number 1, this is generation 2. In the third generation, this is number 1, number 2, number 3, and number 4. So you will say, okay, in generation 2, 3 is affected, and then in generation number 3, you will say generation number 3, you will say number 4th member is affected. So 3, 4 is affected, and 2, 3 is affected. So you should be able to represent this. Okay. So in for the second diagram that we are seeing here, we got again a male and then a female, had 3 kids, and only the son was affected, and the 2 daughters were not affected. Then we go to this one, we can say they're male, female, both were, mom and dad, both were affected, their son was affected, and then what we can see is that this their son got married to another person, and then they had a kid where they had a daughter, and that daughter was not affected. Okay, so if I ask you, in the third generation, was anyone affected? So this is generation number 3. No one was affected. In generation 2, was anyone affected? Yes, the son is affected. In generation number 1, is anyone affected? Yes, both of them are affected. Number 1 is affected, 2 is affected. In generation number 2, number 1 is affected, 2 is not. In generation number 3, 1 is not affected. And then you go to this one, you can again see not affected male marries affected female, have kids, both the kids, male and female, so son and daughter, both are affected. Then the daughters get married, and then they have 3 kids, out of which 1 son is not affected, daughter is not affected, but the 3rd son here is affected. Okay, so you should be able to break this down guys. Now we're gonna now talk about the inheritance pattern for the genetic disorders. So guys, we first gotta understand the classification of these of the genetic disorder inheritance, and guys, this goes like this. So when we talk about the inheritance, we classify inheritance into two different types. One is autosomal, and if you've watched the last video, you understand that autosomal are the first 22 pairs of chromosome which are not sex-linked, and then there's another category which is sex-linked inheritance. When we talk about autosomal and sex-linked inheritance, both of them can be either dominant or recessive. So you can have a dominant autosomal inheritance, or you can have a recessive autosomal inheritance. And same is true for sex-linked. Sex-linked can also be either dominant sex-linked, or it can be recessive sex-linked. So we're going to see that we're going to focus a lot more on recessive sex-linked inheritance and dominant and recessive autosomal inheritance. Okay, all right, guys. So now let's try to see what do we mean by each one. So the first one that we're going to talk about is the autosomal recessive disorder. What is this supposed to mean, first of all? When we say it's autosomal, we mean that it's among the first 22 pairs of chromosome. It does not include the 23rd one. So the disease is coming from any one of the chromosome, going from first pair to 22nd pair. Okay, that's what it means by the autosomal. Then after that, we got to see that it says recessive disorder. So the disorder or the disease is only going to be present if you got a recessive allele. What does that mean? That means, for example, guys, let's say that capital A is one person who has capital A and capital A. Will this person be affected? No, this person will not be affected. So we'll call this person unaffected because this person does not have a small a. So if you have a person who is small a, that person is the one who's going to be affected. That's what we mean by recessive disorder, that both the alleles must be recessive in order to see the effect of the disease. That's what we mean by recessive disorder. Okay, so let's say if you got capital A, small a, will this person be affected? No, this person is not affected. By that we mean this person is not gonna show the symptoms for the disease, but we give them a different name. They're called carriers. They are carriers of disease because they themselves do not have a disease, but they can actually give the small a to the next generation, to their kids, and their kids can then ultimately have a disorder. Okay, so that's why they themselves are not affected, but they are carriers of that defective gene. Okay, right. So that's what we can see here. Let's say this is a parent, and you can see this is capital A, small a, this example right here, and we call them carriers, and you can see that here, that this parent is a carrier. On the other hand, you have capital A, small a again, that's also a carrier. And then they have kids. There are four possibilities. Of course, they make gametes. The first gamete is capital A. The second gamete is small a. This parent also makes a gamete, capital A, and then small a. So we've got four total gametes. We put the mothers here. We're putting the fathers here. And then what you can see is we can do our combinations. Capital A, small, capital A, capital A. The capital A and then small a goes here. Small a and capital A goes here. Small a and small a goes here. So now if we try to evaluate this, guys, we have a capital A, this person is not affected, totally fine. Okay, and then we got these two who are capital A, small a, and we call them carriers of disease because again these kids are not going to show any symptom of the disease, but in their kids they can possibly give the small a, and if their kids in future have small a, then they can have a disease. So that's why we call these two kids carrier. These two kids are just like their parents. They're carriers, but they don't show any symptom of the disease. Okay. Now we got the small a. This is that ultimate kid who is going to be affected. This kid will actually show the symptoms of the disease. So this person will be affected. Okay, that's why we call them affected child, because small a. Now guys, this is specific for a recessive disorder. Okay, now if we try to look at their pedigree analysis, this is one example which is trying to show us an autosomal recessive disorder. What can we notice here? The thing that you notice here is there's something special about autosomal diseases. First of all, autosomal diseases compared to sex-linked inheritance, whenever you have autosomal inheritance, you're going to observe that it's common among both male and female. So there's no bias towards one gender. Both male and female get affected by these diseases, or can be affected. They don't have to be, but both of them can be affected. Whereas in this case of sex-linked inheritance, guys, you're going to notice that males are more affected by, especially if you got a sex-linked recessive disorder. Okay, so what we got here, guys, we got these two persons not affected because unshaded, not affected, no one here in the second generation is affected. We reached the third generation. There's this son who is affected. So these two guys had kids, 1 kid, 2 kid, 3 kid, 4th kid, 5th kid, and 6th kid. And you can see that out of those 6 kids, 2 were affected, male and female. Now you see both male and female are affected by equal proportion. This suggests maybe this is an autosomal disease. Okay, which it is. Now, what else do we see? We can see here that you see that one generation actually shows the disease, whereas the previous generation does not. And this, guys, usually happens if does not have to be like this, but usually you're going to see that if you have a recessive disorder, then it's going to skip some generations and then come back. And in that generation, you're going to see more siblings having the disease, and then the next generation is going to skip again. Now again, this is just a possibility. Okay, all right. Now let's talk about the next category, which is the autosomal dominant. Again, we're still sticking to the autosomal, so that's still the same like the previous example. It's still autosomal, but the disease this time is caused if you have a dominant allele, and this can be troublesome, guys. Now what does this mean? So we got a mother who is not a carrier, so must be small a, because you can see this is a dominant disease. Dominant disease means, let's say if capital A is the disease, then small a is no disease. Okay, so let's talk about different combinations. If you got capital A, small a, this person is going to have a disease because this is a dominant disease. If there's capital A, it's going to mask the small a, and it's going to show up the disease because capital A is there. If you got capital A, of course there's going to be disease because it's a dominant disease. And having a dominant allele is going to cause a disease to show up. The third option is small a. Now this is the only individual who is going to be unaffected because both the alleles are recessive and this disease is dominant. So there must be at least one dominant allele for a disease to happen. Okay, so that's what we can see here. Now, especially for pedigree analysis of dominant autosomal disease, guys, you're going to see that all the generations are affected. So there's no skipping of generations like there was in recessive disorder. Now, let's go back to this example. You got a mother who is not a carrier, that means small a, and then capital A, small a is the affected father. So then we show the gametes, possible gametes, and then we show the combinations possible, and then we made capital A, small a, capital A, small a. What you can notice here is capital A, small a, both are affected kids. They are going to have a disease. But when it comes to small a, you can see these are absolutely normal kids and they are not even carriers. Okay, all right, so that was autosomal dominant for you guys. Now let's see the sex-linked recessive disorder. The very first thing that you guys could understand is how we differently write sex-linked diseases and the autosomal diseases. So when we were as I was showing you here, whenever I was talking about the dominant or recessive autosomal, I was directly showing gametes as capital A and small a, or capital A, capital A. Also, you can see here capital A, small a, and if we go higher, again, same thing, capital A, small a. When it comes to sex-linked inheritance, why do we first of all call them sex-linked? Because they are linked to chromosome X and Y. So the special thing that you're going to notice here is when we're writing down sex-linked inheritance, we always label them as X chromosomes, and then we show capital A or small a. So let me zoom this in so you guys can see this more clearly. So what you can see here is always for sex-linked inheritance, we're going to show symbols XX or XY, and then we're going to show whether that gamete it's going to be produced is going to be capital A or small a, or capital A. For Y, of course, we're not going to show anything because Y is a small chromosome and it's missing most of the genes. Okay, now let's see the pedigree analysis first. What you can notice here very easily, guys, is that most of the males are affected. You can see none of the daughter is affected, but male affected, male affected, male affected. This is the easiest way to recognize that this is a sex-linked inheritance. Because in sex-linked inheritance, males have more chances to get the disease than daughters, because daughters have X and X chromosome, whereas sons have X and Y. So in the case of daughter, let's say, if you got X, and let's say, guys, we're going to call capital A to be normal, and you're going to call small a to be the disease, okay? So you can see that in the case of females, if you got capital A, small a, then this person is going to be absolutely normal because capital A is normal. So capital A is normal and small a is the disease. So for a person to have a disease, there must be, since it's a recessive disease, there must be a small a, so X with a small a, X with a small a, for this female to ever have a disease. Whereas the case of male, it can be X small a, and the other one we know is Y, which does not have any gene for that disease. So this male has a disease already because there is no backup plan. Whereas in the case of female, you can have X capital A and then X small a. So even if there is one chromosome which is carrying the disease gene, there's a backup plan. There's another X chromosome in females which can save them from that disease. So yes, this individual, this female, will be a carrier but does not show any symptom. And guys, example for that is hemophilia. Okay, so this case that we're talking about is a sex-linked recessive disorder. So first, it's sex-linked, so you're always going to show this as XX and XY. And since it's recessive, it means that a person should be either X small a to have a disease, or it should be a male with X small a Y to have a disease. Okay, X capital A small a or X capital A does not have any disease, absolutely normal. Okay, this person is a carrier though. It's normal, no symptoms, but is a carrier. This person is this female is absolutely normal, not even a carrier, because it does not have small a. So let's look at this example again here. We got X capital A small a and X capital A Y. And then they make gametes X capital A, X small a, and then X capital A Y. And then you can see we made the Punnett square. And then we got X capital A, that's one combination. X small a, X capital A, second combination. X capital A, Y, this is third combination. X small a with a Y, that's your fourth combination. So we can see we got two daughters and we got two sons. How do we know this is a daughter? XX, XX. XY, XY tells us these are both sons. So this is an absolutely normal son and is a non-carrier because you got capital A. Remember, this disease is a recessive disease, so there has to be a small a here to have a disease. And if you see this one here, X small a Y, you can see here, because this is X small a, this is the affected son. Okay, now if you see on the left hand side, you got X capital A, absolutely normal female, not even a carrier. When you go here, X capital A small a, this is a carrier daughter who is normal. I mean, in the keeping in mind that this daughter is not going to show you any symptoms of hemophilia, but is going to be a carrier. Okay, so what we can notice here is that we started with a female carrier, so mother carrier, and then the father was not a carrier, absolutely normal. And what you see is in the next generation, so in their kids, the son was affected. So you're going to notice, guys, in the case of sex-linked recessive inheritance, your diseases will move from mother to son. Okay, and you will see that mother will probably not be affected because she's just a carrier, but the son is affected, and so is true here. You see, father, son, both. I mean, father and mother both are not affected, but then their son is affected. Again, same thing happens here. Both father and mother are not affected, but their son is affected. Okay, so I hope, guys, this makes sense to you guys. If it does, that's great. If you guys have any questions, guys, please make sure you email me your questions, and see you guys in the next video.